Okay, so let's stop this quiz thing and show you a result. Okay, most of you have chosen correctly, and the answer, okay, should be A. That means A is not correct. Okay, and the reason is actually explained in option B. Okay, so once you have two operators, A and B, this is a new operator, right? So this acting on this one, that actually means you act in B on F first, and then acting A on this new function, okay? Right. So this one is an operator. So this operator should act on anything that's on the right of it, okay? Right. So if I have a P acting on a wave function, okay. So this is H bar over I, d over dx, and f. If you have two functions, for example, and this p not only acting on this f, this p acting on everything afterwards. Okay, so that means it's h bar over I, d over dx, and this things, right? Or you can also act in this one on another function of this one. So this actually means h bar over I, d over dx. You know, this is a new function. Okay, so this is a function. A is an operator. Okay, right. So this A could be anything, could be x or something else. Okay, right. So that's you know, something that some students can easily make a mistake about this operator. So when we write this one, d over dx, be careful. This one acting on the whole thing, okay? The whole thing forward, okay? Not just acting directly on the right of the, or if you really want to say that this one acting on the, suppose you really want to say, if you really want to say something like this one, so what do you do? So you actually write this one as PF and then put a bracket right here, okay? And G. That means you are acting this P only on this F function, and then put this new function, you know, multiply on the another function, okay? So you need to be very careful, okay? So this one does not equal to PFG, okay? So PFG actually means P acting on this. All right. So today we're going to start this chapter 3. Okay. So now here we're going to have more discussion of quantum operators and quantum measurement, okay, in a more general sense. Okay, so we're going to first introduce like functions of operators. Okay. So this one allows us to translate classical mechanics to quantum mechanics. Okay. Right. For example, we're going to discuss like angular momentum Lx, Ly, Lz. Okay. For example, like this one. Okay. And then we're going to talk about the measurement. Okay. We have learned this like a measurement of x and p, and we can decide a little bit more about the measurement of energy, Hamiltonian, and then more general phase quantity is A, okay, something like this one. And then if we have time, okay, we're going to discuss this iron fast theorem, okay, special case. So this is optional. So and also we can only discuss the special case X and P, okay, not on general operators, okay. Right. And furthermore, if we have time, we're going to discuss some classical mechanics, okay, and like Lagrangian formalism and Hamiltonian, and then we look at the correspondence between classical mechanics and the quantum mechanics and see what's the fundamental relation and also what's the fundamental difference. So that's what we're going to learn in this chapter. We're going to spend about 1 week on this. Okay. Right. So we have learn some basic operators like position, momentum, potential, Hamiltonian, so on and so forth, right? And to summarize, okay, just to recap, we know that if you have a wave function for x, you act in this operator on this one basically just means you are doing this, okay? And we have this momentum operator, okay? So this one is defined as d over dx acting on this wave function, right? So that's what we have learned before, okay? And we also learned that you can actually do a combination of this one. So you can have x squared plus x. This actually means you're acting this one twice on this plus x, okay? So that equals to x and x plus x, okay? You do this one twice. So by applying this one, this way you just multiply x, and then you multiply twice. So this is just x squared, right? Okay. And very similarly, so you can say that you can have x cubic operator acting on this one. It should be just x cubic and plus x. Okay. You can continue this one, so you can actually generate this one to all kinds of powers. So that's a very intuitive generalization, right? You can also have something, slightly more, complex. You can have, for example, a new operator. Let's define a new operator like a V. Define this one as 1/2 times a constant k times this k squared. So what does this mean? So this means actually this is defined as right. That means you acting this one on this one first, and then you times a constant, and then you times another constant, 1/2. Obviously, this way equals to 1/2 k x squared plus x. Right. So this way you can actually form a kind of a function of an operator. You can even have a more complex. You can have, for example, let's say another one. Let's say V1. That can be written as 1/k x squared and plus 1/4, let's say k1 and x to the fourth power. For example, you can have this fourth power term, and then you can say that you acting on this one on per side. You are doing this kx squared plus 1/4 k1 x to the fourth power on this wave function, right? Now this is a lure for summation of two operators. So A plus B, okay, and per side. The lure is that you act in per side, on per side A, okay, and then you do the same thing with B, and then do the summation of this one. So that's the definition of the summation of these two. Okay, so now this is an operator. This is another operator. You call this one A. You call this one B. Okay. So you act the first operator on the wave function, and they act in the second part on the wave function and do the summation. Okay. So that means V1 act on this percent x will equals to 1 over k x squared percent x plus 1 over 4. And x to the first power on percent x. And then obviously this will equals to 1 over 2 kx squared times percent x, right? Plus 1 over 4 x to the first power, okay, times percent x. That equals to 1 over 2 kx squared plus 1 over 4 k1 x to first power times percent x, right? So this is still very intuitive, okay? And then you can generate this one, okay? You can do a generalization. So you can say you can define a function in general, Vx. Suppose you have a function like this one, that's equals to V0 plus V1 x plus V2 squared over 2 factorial x squared plus V3, V2 over 2 factorial x cubic, so x squared, plus V3 over 3 factorial x cubic. You can have many terms, okay? And you can immediately say that this is nothing but just a Taylor's expansion, right? Okay, so this is nothing but just Taylor's expansion of a function. And then you can define a V just equals to a function of this operator as if x is just is a variable, but actually it is an operator. And so what you need to do is to replace that x with this operator. So that's V0, that's a constant, plus V1. And now instead of x, you put a head right here, this operator. And then you can have V2 over 2 factorial and x operator squared, and V3 over 3 factorial and x cubic operator. You can do this one. So this is the definition, okay? And then you can immediately say that if you act in this one on a wave function, just follow the same procedure we have done with the simple example we had before. So this will equals to nothing but just Vx times percent x, right? So this is a way that the potential, right? So you can have a potential energy operator, okay? Introduced like this, okay? Right? Okay, and you can do the same thing for momentum operator, even though it's a differential, but if you write this one as an operator, it will be perfectly, of the same formalism, okay? And then you know that you can have P percent x that equals to h bar of I d over dx percent, okay? Of course, you can define P squared over percent x that equals to, you do this one twice, right? Okay, so that would be nothing but just h bar of I squared and d squared over dx squared per side. You do the differential twice, okay? And you can also have an example. Okay, the kinetic energy that equals to P squared over 2m. Okay, and then you know that K acting on this psi is nothing, just equals to minus h bar squared d squared dx squared. So that's over 2m. And on this psi function, right? So that is a kinetic energy operator. Okay. And then of course you can again have even a combination of both function of x and a function of p. Okay. So you can make this one to be even more advanced. Okay. You can have h equals to, for example, k, the kinetic energy, plus the potential energy. Okay. That equals to, for example, p squared over 2m, and plus a function of x operators. Right. So there are different examples. Okay. So we consider, say, a harmonic oscillator. Okay. In this case, we know the kinetic energy is just p squared over 2m, and then the potential energy is m omega squared over 2 times the x operator squared, right? Okay, so that is the harmonic oscillator. Okay, a free particle, that's another trivial case, right? Okay, in this case, the Hamiltonian is just very simple. Okay. You can have a nonlinear oscillator. Right, you can have h equals to, for example, p squared over 2m. That's kinetic energy. You have a potential energy, but this potential is nonlinear, so you have the usual one, m omega squared and x squared. This is just a harmonic oscillator. But now you can have higher order terms, 1 over 4. Say you can have, k prime, just a constant, times this one to the 4th power. Okay. So in this case, you have, non-harmonic terms. Okay. So that one will lead to higher order correction to this harmonic oscillator. Okay. So you can have many other things. Okay. Right. So anyway, you can have different kinds of combinations of these operators. Okay. And let me give you another example. Okay, so that hopefully not to confuse you, but try to get you more familiar with the operation of operators. Okay. Right. Let's use this p operator again. Right. Let me just write down this as h bar of I d over dx. Okay. So you know this one. That's a definition. P psi x that will equals to h bar I d over dx psi x, right? And let's try to form a kind of function of this one. Let's say, for example, you can have the nth power of this one first. What would be this? By definition, this will be do this one, just m times, right? On this wave function, okay? So you do this one first, and then you do this, 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 right? So that's the definition, okay? You just put that one into this, so you got the h bar of I. This is a constant to the nth power. You do this one m times. Very nice, right? So the p to the mth power acting on a wave function is just you do the differential, to the nth order, and times the constant h bar over I n times. Okay. Of course, you can have a function of this p operator. Say, let me write down this one as f0 plus f1 and p, and then plus f2 divided by 2 factorial. Very similar to the Taylor expansion, and fm 3 factorial and p cubic and so on and so forth, right? And then you can do the same thing. What will happen if you apply this P acting on this percent X? What will be the result? Of course, you just put this one 10 by 10, right? Okay. And the first term will just give you F0 times percent, right? And the second term, you know that this is going to be F1 H bar Fi d over dx percent, right? And then the third term will be F2 over 2 factorial and H bar Fi d over dx to the second order. And then you have the third order, F3 over 3 factorial and H bar Fi cubic, and do the third order derivative and percent, and so on and so forth, right? Okay. So basically, this will be just F0 plus F1 H bar Fi d over dx and plus F2 over 2 factorial H bar Fi squared d squared over dx squared, and then plus F3 over 3 cubic H bar Fi to the third power d cubic and over dx cubic. Okay. And acting this one on percent x. Right? Of course, there are higher order terms if there are more terms. Okay. So this is something that's a derivation of a function of this operator. Okay. Right. And let's consider a specific example. Let's say consider, for example, EI a constant, say A times this operator divided by H bar. Okay. I'm trying to use this constant that so you can see that I define this one as FP. Okay, first, and this A is a constant. Okay, and of course you can see that if you want to have a dimension of this. So you know that this must be a length. Okay. So A is a constant length, right? Because it has a dimension of length. Because the Planck constant has a dimension of length times the momentum. Okay. Let's do the expansion of this one. Taylor expansion. But definition this one should be 1 plus IA over H bar and the P, right? And then plus 1 over 2 factorial I over H bar times A squared and P squared. You can go to higher order terms, okay? All right, so these are the definition of this exponential function of this operator, okay? And let's see if we apply this one to a wave function, see what will happen, okay? Let's apply this one to a wave function. See what's the result. By definition, this should equal to 1 plus I over H bar times A and then P plus 1 over 2 factorial I over H bar and A squared and P squared and plus higher order terms. Okay, all of these terms plus X, right? We can just do this one by one. So the first one will be just plus X because it's 1 times plus X. The second one will be I over H bar times A times H bar of I d over dx and percent, right? Because that's a P operator, it's just H bar of I times d over dx. And then the next term is 1 over 2 factorial I over H bar times A squared. And then P squared is I over H bar squared and D squared over DX squared and plus X, right? You can do, for example, one more term to get this one, the more inspiring. So you can have this one to the third power, and the H bar of I to the third power, and do the third derivative of this wave function, okay, and so on and so forth. And now you can see that, yes, of course, this H bar cancel this H bar, this I cancel this I, right? And this I cancel this I, this H bar cancel this H bar, and this I cancel this I, this H bar cancel this H bar, okay? To simplify this one a little bit, okay? Okay, and then this will equals to percent X plus A d over dx percent, and then plus 1 over 2 factorial A squared d squared over dx squared plus X, and plus 1 over 3 factorial A cubic d cubic over dx cubic plus X, plus so on and so forth. Okay, so guys, can you recognize this term? So this one basically, you are trying to do this one. The first one is nothing but just percent X, right? And the second one is just A plus percent, the first order derivative. And then second is just A squared over 2 factorial percent prime prime. And then the third thing is A cubic over 3 factorial percent prime prime prime. And so on and so forth. So you can see this is nothing but just a Taylor expansion of percent X, okay? Right? So if we do the summation for all of these terms, this will simply just be percent X plus A, okay? So what's the meaning of this? So what's the meaning of this one? What's the result of this? So that means EIA times A over H bar acting percent X will just equals to percent X plus A, right? Or in other words, you can put this one to be minus IA P over H bar acting on this percent X. That of course will be just equal to X minus A, right? So what's the meaning of this one? What's the meaning of this one? Suppose you have a wave function. So this is percent X. And then what you have done is that you apply this one to this. So you got a new wave function. The new wave function will be, it's just shifted by A. Okay, so that means EI minus IA, the P operator over H has a very nice physical meaning. It's just a displacement by A, right? So you can see that this is quite some fun, okay? So you can define an operator, and then you can build up on that one by some combination. And a very nice explanation is the exponential function of this operator. Now you can see that it's just a displacement of this momentum operator, okay? So I give you an exercise for you to try later, okay? If you're interested. So exercise How about this one? Okay, what's the physical meaning? Okay, so you're encouraged to try this one later once you have some time. Okay, right. And we also know that these operators X and P, they do not commute, right? Right. So you activate these functions, and actually specifically, you know that X P acting on percent X will equals to X H bar of I d over dx and percent. That equals to just H bar of I X and the first order derivative of percent. But Px on this one, actually, so this is the quiz problem we have done, okay? H bar of I, d over dx, and x percent, right? But now this d over dx is acting on everything just follow it. So it acts not only on percent, but also on x. So you got two terms using differential by part. So the first term will be just h bar of I and percent, right? So if you apply this differential just on x, or you have another term, h bar of I, x percent prime. So you can see this term and this term are equal, but you have an extra term, okay? So if we do the difference, so you can see that so you actually have this two terms, this term and this term cancelled, okay? But you have an extra term, that's minus h bar of I percent. So this is just I h bar acting percent x. So you can see that this is correct for any kind of wave function. So that means this operator, if you take this one as an operator, is nothing but just multiply a wave function by I h bar. So in this sense, we define the commutators. Okay, so this one equals to x p minus p x. Okay, so this one just equals to I h bar. So that's the definition. So this one equals to I h bar. Okay, and so for the commutators, for any two commutators, this one actually can be generalized to be any two operators. It's just defined by a b minus b a. Okay, and so we are going to encounter such kind of commutators again and again, okay, in quantum mechanics. And actually, this is the most important algebra in quantum mechanics. So this one equals to, that's not equal to the commutator between B and A, okay? So if we change the order is important. If we really change the order, so there's a minus sign right here, okay? You need to be careful with this, okay? To get more familiar with this one, let's try to evaluate a few operators like this one, 1, and 2, this one, and 3, and such kind of things like this one, just as examples, okay? Let's consider the example 1, okay? What's the commutator between this x to the nth power and the p operator? So what we need to do is to apply this one on a wave function and see what will happen, okay? So this will be x to the nth power and p on this wave function. So this one, of course, is just x nth power, h bar of I, and then you have d over dx percent, right? So it's nothing but just h bar of I, x nth power, and percent prime, okay? And then if you do this one, you should act x on this percent n times first, right? So that is h bar of I, d over dx, x to nth power and psi. And now this differential can act on this one first, and then on this one, okay? You do a differential by parts. So that will give you one more extra term, that's h bar of I. This is a factor of m, and x to the m minus 1 power and psi. So this is the extra term, okay? And then you have the term that's equal to the original one. The one, if we do a differential on psi, okay? And then of course you do the difference. So this one minus this one. So this term will cancel. So you got just the extra term. Psi, sorry. Right, so that's equals to I h bar. Okay, if we do the difference, action psi. So you got this action, that's nothing but just minus I h bar of I and m times n to minus 1. Okay, action psi. So this one just equals to I h bar m and x to the power m minus 1 action psi. And this one just equals to I h bar m and the x operator to the power m minus 1 act on this psi, okay? So that's the action on the wave function, okay? So this one should equal to this, right? So that means, this one is correct to all wave functions. So that means this commutators between x operator to the nth power and the momentum operator should be nothing but just, I h bar m and x operator to the power m minus 1. Okay. And you can check if n equals to 1. So this one is just a special case of this, right? Okay. You can actually generate this one to other terms, okay? For example, you can have a times x for example, the force power and the p. And this a is just a constant. You can see that this one equals to a x to force power times p minus p a x to the force power. But you know that this a is a constant, so you can move this a freely to the left. Okay, so that will equals to a and the x to force power p minus p to the x force power. So that means this one just equals to a, the commutator between x to force power and the momentum operator p. So that will be, as we have done before, so it will be just equals to a times h bar and I h bar and 4 times x to the cubic. So this one can be generalized to all summation. For example, you can have a x to the fourth power plus b x to the sixth power and the momentum of this one. So you can do this similarly. You can do the commutator between this one and the p, and then this one, this, right? So you can simply just do the summation of this. So you can have a x to the fourth power and the p plus b x to the sixth power and the p. And then this will equals to 4 I h bar a x to the cubic and plus 6 and the b I h bar x to the fifth power. Okay, you can continue this one, so on and so forth. So you can have, for example, have a Vx just equals to V0 plus V1 x plus V2 over 2 factorial x squared, and so on and so forth. And you can try this. Okay, and this one, of course, will just equals to V0 P and plus V1 X P plus 1/2 factorial V2 X squared and the P, and continue right this way. So this is a constant, this is momentum, okay? A constant and momentum, they commutates because you can say that, for example, this is V0 and the P just equals to V0 act on this, the times this operator and the minus P and this one. But this one is a constant, so there's no effect on this one, right? So this just equal to 0, okay? Okay, so then you just follow this. You find that this one just equals to 0 plus IH bar V1, right? Because X and the P operator is just, the computer just IH bar, so you got this one. And then second will be 1/2 factorial, and that's V2, okay, constant, times IH bar, times 2, and times X n minus 1, that's 2 minus 1 is 1, right? And the third term will be 1/cubic V3 and IH bar and times 3 times X squared, so on and so forth. So if you look at this one, this is nothing but just you put an IH bar right here because every term has this term. What's inside is going to be V1 plus 1/1 factorial V2 times X, and then plus 1/2 factorial V3. Now this one is X squared, and so on and so forth. So what's this one? So this is nothing but just a tiny expansion of the derivative of this one. So it's nothing but IH bar, the derivative of V, that's V prime, as a function of X. Okay. So this is a very nice formula, right? So you can not only have commutators between X and you can also have XM and P. You can also have Vx, a function of X and the P, okay? As another example, we can check, say, let's look at the X and the P squared. What will be this? Okay. Again, we can write down this as X P squared on a wave function. So this will be X I over H bar squared and D squared over DX squared on this percent, right? Okay, so that's the, so this one will be nothing but just H bar over I squared. And then this will be X, you know, D squared over DX squared and the percent, okay? And then this one, we know that we need to have X acting on this wave function first. So that will be equals to P squared and X percent, right? And now you can have D over DX on X percent. And this H bar over I squared, okay? And then again, use the differential by parts. Okay, see what will happen, okay? So you're going to have H bar squared over I squared. So you can have, of course, do this one twice all on this one. Okay, or you can have this one all on this, right? Or you can have D over dx on X and D over dx on percent, right? Okay, you can have something like this one, and we know that this one is 0, And this one will give you 1, okay? So result is going to be h bar of I squared, d squared over dx squared, and percent, okay? So this one is the same as this one, but now you have an extra term. The extra term will be 2 over d over dx and percent x, right? Okay, so you have terms like this one, and then by look at the difference between these two. So you can immediately identify. So this one is the term. So that one is actually h bar of I d over dx percent. But now you have a factor of 2 right here. You have h bar right here. So this is new term, right? So if you compare these two, so look at the difference. So this is nothing but just I h bar 2 times p. Okay. So you can do the same thing for x and the p cubic. Okay. So you can check using very similar procedure. Okay. You find that this is nothing but just m. To nth power, sorry, m times I h bar and the p to power n minus 1. Okay. I leave this one as an exercise for you. Okay. So this one you can actually, you can see that by using this x and the p commutators, you can look at the commutator between any of this one. So you can even a more difficult exercise. So you can have a difficult exercise. Okay, so this one equals to what? Okay, so if you work this out, you'll find that yourself is actually quite familiar with this kind of things. Okay. All right. So let's take a break at this point and see if you have questions. All right. And now I want to give you another example. Hopefully this is more interesting. Okay. So we know that you can have a combination of operators. Okay, of different operators, and then form a new operators. Okay. First of all, let's try to generate this one to 3D cases. Okay. Right. The generation to 3D actually is very simple. You can have x and the px. Now it's just h bar of I partial over partial x, and the y, of course, and py that equals to h bar of I partial over partial y, and c and the pc equals to h bar of I partial over partial c. Now you can say that all of this thing have the commutator as we had in one-dimensional case, right? Okay, C and PC. Of course, this is intuitive, right? You must have this one, because if you just look at the one motion, the one-dimensional motion in the x direction, y direction, z direction, they should be the same, right? So that means they should have the same commutators. And also, you can find that for others, for example, the commutator between x and py and pc, okay, this one should be 0, okay, and similar for the y and the px, py and z pz, px and pz and z for px and py, right? And also you have the mutually the coordinates. Right. Okay, so they all commute. Okay, so because you know, just for example, you can look at the px and py on per side. That will equals to h bar of I partial x, h bar of I partial y on per side. Obviously, the differential with respect to y and the differential with respect to x, they commute, right? So that means this equals to h bar of I partial y, and then h bar of I partial x on per side. So that is nothing but just py and px per side. Okay, right. So this is the example to show that indeed they commute, right? Okay. And now we are ready to, with these operators, you can form combinations. Okay. Right. We know that in classical mechanics, okay, we have for angular momentum L that equals to R cross the momentum P, right? So you have three components. So this one equals to, if you say that you have EX, EY, EC, three unit directions in the X and Y direction, and then you have X, Y, Z, and the PX, PY, PZ, okay? So you have three components. And then the first component in the X direction, for example, is going to be EX, this X direction, and that is Y times PZ minus Z times PY, right? Okay. You have the Y component. Okay. So you just change Y to be Z and Z to be X. Z times PX minus X times PZ. Okay. And then you have a Z component. You just change Z to be X and X to be Z to be Y. Okay. So that's the definition of angular momentum in the classical mechanics, right? Okay. Now let's just say, just guess. Let's just form, okay. In quantum mechanics, the operators. Can we say that this one just equal to the operators of these operators? So what does this mean? Does this mean we have also EX, EY, and EZ? That's the directions. But now this one will change to be operators. Can we do this? So that's a problem, right? But there's an immediate difficulty or problem in general in the translation, okay? So if we have a classical mechanics and translate into this quantum mechanics, okay? So basically you can say we change X into the operator, Y into the operator, and Z into the operator. That's easy. And the PX into the operator, that equals to H bar of I partial X, right? PY become an operator. All of this one are good. Okay. But we cannot do this one arbitrary. For example, there's a difficulty. So for example, if we have x squared times px squared in classical mechanics, okay, suppose I have something like this one, and then you do the translation, there are different ways. You can say this one can equal to x squared and the px squared, okay? But in classical mechanics, this one also equals to px squared and x, right? And this one will equal to translate, if we write this one directly. But these two are not equal, okay? And this one, you can even have something like a p squared and x squared, right? And this way you do the translation will be px squared and x squared. And this two is not equal to this one, right? So that means when you're trying to translate the quantity in classical mechanics directly into quantum mechanics, so there could be a problem, okay? Right? Because once you have a combinations of different operators, okay, there is a question of the order. How would you put the operators in order? Which one should come first? Which one should come later? Okay. So then we should choose which one. That's the question. Okay. And the answer is that one has check with experiments. Okay. So you can do this kind of translation. But then there is some kind of arbitrariness in deciding this order in quantum mechanics, because different orders means different things, right? They're not equivalent. So to make sure this one is the right translation, the only way you can check, it's not theoretical, okay, is that you have to compare your results to experiments. If they are consistent with experiments, and then it's okay. But unfortunately, if we really do this one, you find that, okay, suppose we just do this one naively, look at just one term, okay? Y and PZ minus Z and PY. So fortunately, these two commute. These two also commute. So you don't really have an order problem, right? And the other terms can be just written similarly, okay? So fortunately, no order problem. Okay, so this one is called the order problem, okay? In the translation, okay? Right, so there's because the order is not fully determined, okay? So we have to check with the reality of the experiments to decide whether the choice of the order is correct or not, okay? All right, so then, since fortunately in this kind of a combination of operators to form the angular momentum, we don't have this order problem, so we can just naively write down this operators. Okay. Defined as Lx just equals to y pz operator, of course, and z and py. That's nice. They do not have this order problems. And Ly equals to and z and py x minus x pz, and Lz equals to x and py minus y px. Okay. So there's a nice property of this cyclical. You can see that on this one, this is x goes to y and it goes to z. In this one, okay. In this one is y goes to z and it goes to x. And then in this column, this is z goes to x and then goes to y, right? And this one is z goes to y and goes to x, sorry, and it goes to y. And this one is y goes to z and then goes to x. Okay, so this one is kind of there's a cyclical, rotation in the direction. Okay, so if we change x to y and then y to z and z to x, you can obtain the definition of Ly from x and the Lz from y, right? So this one can be summarized as just one. So suppose this one is just like denote Lx and Ly as 3 components. Okay, and I defined as x, y, and z 3 components, and the p operator similarly has 3 components, x and y and z. Okay, and with this kind of cyclical relation, you can see that so this can be just written as a very compact way, just as we had in classical mechanics. Okay. Okay. Right. So that's the definition. Okay. And this kind of definition has a very interesting things. Okay. First of all, you can see that let's see the commutators, the dimensions of this one. Now we know that this dimension, that of course equals to dimension of R and the dimension of P, right? Okay. So this is the same as the dimension of H bar. Okay, so this is one thing that's interesting, okay, about this angular momentum. Okay. And secondly, there's another interesting about this momentum. So if we make this R goes to negative R, and the P goes to negative P. In physics, we know that this one is called inversion. Okay. If you do inversion, okay, suppose you just do inversion of the space. Of course, the position will just go to opposite, and the momentum will also go to opposite. But the angular momentum, look at this one, they're equals to. So that will transfer to minus R cross minus P. And this minus and minus cancel each other. Okay. So this one is invariant. Okay. So in this case, we say that this one is called a pseudo vector or actual vector. Okay. That's a very nice, a very interesting property of this angular momentum. Okay. Right. So we're going to later we're going to use this property of angular momentum. Okay. Interesting property of angular to form, for example, Hamiltonian. Okay. Anyway, so this is the a nice, interesting property of the angular momentum under, a transformation called inversion. Okay, so if we change R to minus R, P to minus P, but L will not go to minus L, it just goes to L. Okay. And now let's examine the commutators. Okay. So that's another interesting thing. Okay, between, say, for example, Lx and Ly and Ly and Lc and Lc and Lx. and so on and so forth. These are the three interesting operators. Okay. And we know that for the momentum, we know that for this one, x and y and z, for the position, okay, and c and x, this one all 0, right? And also we know that px and py and py and pz and pz and px, they all commute. Okay. So this one equal to 0 or not? Do they commute? Okay. So that's another interesting about this angular momentum operators. So let's check one first. Okay. Lx and Ly by definition. Okay. So that's y pz minus z py and then z px minus x pz, right? So there will be 4 terms. Let's check this one by one. This one and this one, they will, because this one is a differential with z, this one is differential with x. So the result is going to be yz h bar of I squared partial z partial x. That's the first term, right? And then this and this term, that will be also very simple. It's xy h bar of I squared partial z squared. Okay. And how about this term and this term? So this will be minus z squared partial x partial y. Let's see. Sorry, I made a mistake. I made a mistake. Okay. All right. Let's look at this one and this one. Okay. Because there's a z right here. Okay. So this, the first one will be y h bar of I partial z. And now this has c h bar of I partial x, right? That's the first term. And then this one, that's simple, okay? So minus xy h bar squared of I squared partial z squared, okay? And then this one and this one is also simple. So that's minus z squared h bar squared of I squared partial x and partial y, okay? And then the last term is also, let's say, so this one, that will be plus xz h bar squared of I squared partial y partial z, okay? Right, so this one and this one commute, this one and this one commute. So the only one that's not a commuter is this one. Is the y times pc and the z times px, okay? So this one will give us one extra term, okay? So that will be h bar of I and then you have y times h bar of I partial z, right? So this is an extra term. And then you have the order changed, okay? So that will be yz h bar squared I squared partial z partial x, okay? So this term will lead to 2 terms, okay? And then this term 3 terms are just okay. Okay. And then you can do the same thing for Lx and Ly. Change the order. You know that once you change the order, the only thing that is that now you can not going. So this term actually this one will be fine, but you're gonna have another term, right? Let me do the. Okay, let's move this one down a little bit. Okay. Let's compare this. Look at this one. This one will equal to, just change the order. That will be Z Px minus X Pz. Okay. And then Y Pz minus Z Py. Okay. So again, you can look at the terms that commute, right? So this one and this one commute. This one and this one do not commute, and this one commute. Do not commute. Okay. So let's say. Okay, let me do this way. Okay, let me do this way. Write down this as Y Pz Z Px, and then you have plus Z Py X Pz, and you have minus Z Py and Z Px. Okay, and then minus Z Y Pz and Z Px, right? So you do the expansion, and this one you have Z Px Y Pz, okay? And you minus and plus X Pz and Z Py, okay? And also you have minus Z Px and Z Py, and then minus X Pz and Y Pz. Okay, if you compare this one and this one, let's look at the difference. Okay, so this is because there are many terms, so we need to be slightly. So look at this one. This is X and Y, Pz and Pz. So that means this term, X and the Y. Where's X and Y? We Pz and Pz. Oh, so I think there's okay. Let's see. This is Y Pz Z Px. Okay, that's the this term and this term, and then Z Py X Pz, right? And then you have Y Pz minus that, okay, and the X Pz. Sorry, yes, and then this and this. That's minus Z Py and Z Px. Okay, so if you compare these two terms, you can see that this term is the same as this term, right? Because all the terms here commute, and this term, okay, is the same as this term, so they will cancel, okay? Right. And then the terms that do not simply commute is one is this term, and these two terms will have extra term, and these two terms will have extra term, right? So you look at this one, look at the extra term first. So you can see there's a PZ right here. So if we do the commute, so this one will equals to, you know that PZ and the Z will equals to, of course, Z, the commutator, sorry. So equal the commutator PZ and Z plus Z and P, right? So that means this term will be equal to, say, which term? XZ, and this one will equals to minus I H bar, right? Plus ZP. So basically, if we change the order, you got an extra term, minus I H bar right here, okay? All right. So the difference will be, so you have the difference Lx, Ly minus Ly and Lx. So you got a difference term. That will be I H bar X times Py, right? So that's let me use different colors. This term comes from here, and this one, right? And then you have another term Zp, and then Zp will simply just cancel this term, right? And then similarly, you can do the same thing for this one. So here you have Pxc, and this one again you can write down this as minus I H bar plus Z and Pz, right? Okay, and then you compare this one and this one, okay? They will be the same, okay? But you have an extra term, okay? So that means you got a term become I minus IH bar. But now this is going to be Y, because this you have Y right here, you have PX right here. So Y and PX, okay? But anyway, you need to be a little bit careful with this kind of calculation, okay? There are many terms. But anyway, and the result is very nice. So it's Lx and Ly commutator just equals to IH bar XPy minus YPX. Okay. And if you look at this one, this is just the definition of the C component. Okay. Right. It's just this one. So that equals to IH bar LZ. Very nice. Okay. And then you know that there is a cyclical relation because X to Y, Y to Z, and they have Y to Z, Z to X. So that means if we do the same thing right here, so you should expect we can have this rotation. Right, you change X to be Y, Y to be Z, and then Z will be X. Because in the definition, you have this kind of rotation, right? So then you have LZ and LX you change y to be z and z to be x, and then x will be y. Okay. So you have this very nice rotation relation. Okay. So this is the commutators between the angular momentums. Okay. So they are very different from what you have for this position and the momentum operators. Okay. All right. So what you need to do is do this kind of calculation. So you can try to do some exercise on this one. Try to use the derivation and do this one turn by turn and to see whether you can verify this one. So we have done this one, okay, with a lot of mistakes, but eventually we figured out, right? Okay. And you can also define the total angular momentum. Okay. That is Lx squared plus Ly squared plus Lz squared. We use a shorthand notation called this one L squared. Okay. And then you can also check that very interestingly, Lx and L squared, this will equal to Ly squared, Ly commuted and L squared, Lz and L squared. This will equal to 0, okay? And so this one can be done, can be proved just using Lx, Ly equals to I h bar Lz, and they are cyclical relations. Okay, you just change x to be y and y to be z and z to be x. Okay, and that's x's as well. Okay, so this is another thing about this angular momentum. Okay, but to get this one a little bit more interesting, let's examine the specific form of L, X, Y, and Z, for example. We know that, for example, Px is given by h bar of I partial x, right? So on and so forth. And how about this one? Oh, this one. And this one, okay? So we can see that, for example, Lx equals to C, so y times Pz minus Z times Py, right? So specifically, this one can be written as y h bar of I partial C, and then minus Z partial y, okay? And Ly, of course, will equals to h bar of I and Z partial x minus x partial Z. And Lz will equals to h bar of I, and this will be x partial y minus y partial x. Okay, so that's a specific form. Okay, but not very intriguing. Okay, and to make this one to be interesting, let me consider just one component. Okay, just consider Lz. That's h bar of I x partial y minus y partial x. Okay, but now I'm going to use cylindrical coordinates. Okay, so we define x equals to rho times cosine theta, y equals to rho times sin theta, and z still equals to z. Okay. right? And from this one, you know that, for example, you can have a partial y where equals to, partial theta partial y, and then partial theta, right? Plus partial rho partial y, partial over partial rho. And of course, there's a C component that you don't need to worry about that. And partial y, x, equals partial theta partial x, and then partial over partial theta, and plus partial rho partial x, and then you have partial over partial rho. Okay. Right. And this one, of course, you also have rho equals to square root of x squared plus y squared. Okay. And theta just equals to the arctangent of y of x. Okay. So you put all of this one into this one. So the result actually is very interesting. You have LC can be written as h bar of I partial theta. So this is something very interesting. So you can see that so this is like a momentum operator, right? But on angular variable. Right, so if we compare this one, we know that x and the px were equal to h bar over I partial x. But now you can say that now we have an angle variable, and then you have LC. That's nothing but just h bar over I partial theta. And this is a very nice relation, right? Because you can remember we can define. So this is x, this is y, and this is c. And now you can define the angle. So this is rho, and this one is theta. So you can see that once you change this theta, okay, so you have a velocity along this direction, right? So it's like you have angular momentum about the z-axis, right? So you can see that the motion, okay, along theta is just a rotation about z, right? So that's why. So this one gives us a very good confidence of assignment of this one called the angular momentum, right? Right, because this differential, okay, it's very similar to the definition of the momentum, but along the x direction. But now this is very much like a momentum along the angular direction, okay? So we know that the motion along this theta, if we don't change more, if we don't change c, so this motion will be purely rotation about the axis, right? So that means you have angular momentum instead of a momentum, okay? Right. So this gives us some kind of sense, okay, about this definition of angular momentum, okay? Right. Okay, I think we should stop here today. Let's say if you have any questions. So basically, the derivation of this is inserting, this 1 and 2 into that will give us LC equals to H bar of I and partial theta. So can we evaluate Lx and Ly by the commutator by breaking it into smaller commutators like we did in classical? Yes. And so that's another way to do it. So you can do the expansion. You can also do something like this one. For example, you can have A plus B and C plus D, right? These commutators. So this one, you know, actually can be written as A and C plus A and D and plus B and C and plus B and D. Okay. Yes, this is correct. And then you can do, for example, for Lx and Ly, you can also do like this one. So you can have so basically this you have Y and PC, right? Minus and C and PY, and you have say C and PX minus X and PC. Now you can make this one A, this one B, this one C, then this D. Okay, so that will have 4 terms: Y and PC, and C and PX, and then plus Y and PC minus X and PC. So this is the last way to do it. You're right. And the PY and the C and the PX and plus minus C and the PY and minus X and the PC. Okay. And then you can say that because Y and the X commute, Y and the PC commute, PC and the X commute, PC and the PC commute, so this one is 0. And you have C and the Z commute, okay, Z and the PX commute, PY and the Z commute, PY and the X commute, so this one is 0, okay? And then you have only thing left is these 2 terms, right? But you have Y commutes with everything else, and the PX commutes with everything else, so the first one will equals to Y, and what's left is PC and Z. This is a little bit quick, okay? And then the last term is, again, you have PY commutes with everything, so you can put PY anywhere you want. And this will be minus Z. And then X is also, you know, can put it for anywhere, right? And this one gives you minus IH bar. This one gives you IH bar. So the result is IH bar and X PY minus Y PX. Okay. That's also a nice way to derive this one. Okay. So here I was a little bit quick. Let me expand a little bit more on this one. So Y PC and Z PX. So you look, the Y is commutes with everything else, right? So this one can be written as, for example, Y PC and Z PX. Okay, because this one commutes with this one, so you can move this one here. That's freely. And this one commutes with this one, so you can move this one freely. So this one basically equals to Y PX, okay, PZ and Z, right? You cannot change the order of this one. This one must be kept the same, okay? And then another thing is minus and Z PX and Y PZ. And again, this one commutes with this one, right? So you can move this one also. And this one commutes with this one. You can also move with this one. You can move this one to anywhere, right? So you can put this one to be Y minus Y, sorry, PX. And then what's inside is Z and the PC, okay? So you cannot change the order of this one because these two do not commute. And then you can combine the two. Okay, so that will give you, y, px, pj, and z minus z, and pj, right? Okay, so this is just this term. Okay, you're right. So you can also, do this one slightly more quickly by using this formula. Okay. Any other questions?